Hey everybody, in this little video we're going to talk about an example involving trigonometric substitution. Alright, so here's the integral that we want to solve, and we know that because the integral has the form a squared minus u squared, that this means that we're going to use the technique involving a sign substitution. Alright. Okay, so what we're going to do is we're going to first set up our triangle, so I'll do that on the side over here. With the sign substitution, we're always going to put the square root as the base of our triangle, which leaves the hypotenuse to be 3 and the height of the triangle to be x. And this is our theta in here. Now from this triangle we see that sine of theta is x over 3. So that leaves x to be 3 sine theta. And from there we can take derivatives to find what dx is. And a few other things we're going to need from our triangle. So these are the main things that we need. A few other things. We want to solve for theta, so we use this equation. And we solve for theta, we find that theta is arcsine of x over 3. Alright, and we also know that because our main integral involves the square root of 9 minus x squared, from our triangle, if we can get an expression for that radical, that would be very helpful for us. So I notice that if I take cosine theta, you're going to get the square root of 9 minus x squared over 3. And solving that for the square root of 9 minus x squared, we have the square root of 9 minus x squared is 3 cosine theta. Alright, so this is going to come in handy. This blue piece is going to come in handy. And then each of the terms in the black box will also come in handy. Alright, so let's move back to our main integral here. And we're going to perform our substitutions. So x squared is going to stay the same for now. We're going to replace the square root of 9 minus x squared by what we found for it, which is 3 cosine theta. So we have times 3 cosine theta. And then finally for dx, we replace dx by what we found for dx, which is also 3 cosine theta, d theta. Okay. Now we notice that we still have an x squared here, so we use the expression for x that we found from our triangle in our main equation here. And when we do that, when we do that, we're going to find that this is the integral of a 9 sine squared theta times 9 cosine squared theta, all d theta. Okay, and so therefore that's 81 times the integral of sine squared theta cosine squared theta d theta. Okay, so this is the kind of the basic step here. Now we have to figure out how to complete that integral, and that's what I do in the next video in this sequence. Alright, I'll see you guys there. So the first step is going to be to use a Pythagorean theorem on the sine squared term here. Alright, and then we're going to expand this expression. Then what we're going to do is we're going to split the integrals. And we have to treat these two integrals separately. So the first integral on the first side, we're going to use a power reducing, or in other words, the half angle identity. And we can then treat each of these two integrals separately. So you end up with theta over 2 plus sine of 2 theta over 4 after we do a little substitution with that integral. Okay, and that leaves just this integral to worry about, and that's going to need integration by parts. Okay, so let's move on over to treat that guy separately. So we have the integral of cosine to the fourth of theta d theta. We're going to let u be cosine to the fourth of theta, and we're going to let v prime be 1. And let's see what that does for us. So here's what here's our choice. We take a derivative of cosine to the fourth. We get 4 cosine theta times negative sine theta. So we have a negative sign out front here. And we integrate v prime to get that v is theta. So this is what we compute. So integration by parts, the rule says the following. And we figure out what we had here. So we have theta cosine to the fourth of theta minus the integral of theta